Okay, so why do we need power? Why do we need 1 minus beta, right? Well, remember conditional probability back in the day? Well, here it's going to come back. Those concepts come right back. Remember the idea that, sometimes we want to detect some sort of disease, right? And we might give a test, right? Like, for instance, we want to know whether someone has HIV. And so we give them a blood test to figure out, do they have HIV? Now, these tests aren't perfect. And so there's some chance that they'll be able to detect this disease and some chance that we'll make a mistake. There's two ways of thinking about this prediction. One is what we call a positive predictive value. We could think about what is the probability that someone has the disease, for instance, HIV, given that they test positive, right? Well, this will help us know what is the chance that they actually have the disease once we know their test score. In this world, we know their test score, and we want to know what's the probability that they have the disease. On the other hand, we have what's called sensitivity. Sensitivity thinks about the world in a slightly flipped way. Given that this person has a disease, has whatever disease, such as HIV, what is the probability that they will actually test positive, right? And so these two actually give us very different worlds. In one world, the given is that they have a positive test. And what is the probability that they have the disease versus no disease, right? In this scenario, the given is very different. The given is that they actually have the disease. Given that, what is the probability that they'll test positive versus negative, right? And so they're looking at this or they're looking at this, right? Now, power is basically the probability of getting a hit, the probability of rejecting that null hypothesis, given that the null hypothesis is actually false, so it's actually wrong, right? Is this more like PPV, positive predictive value, or is it more like sensitivity? Well, let's think about this. In this world, there's this reality that the given reality is that this is false, right? We need to reject it. We need to reject it. What is the probability that we'll actually reject it? So reject or fail to reject. Well, one way of thinking about this in a more in this comparison is to consider really what is the thing that we don't know in these two scenarios. We don't really know if they actually have HIV. We know their test. We know that their test is either positive or negative. And the test is uncertain. But whether they actually have HIV or not, that doesn't have uncertainty. It's just that we don't know what it is, right? This is sort of like HIV in that way. This is the reality, right? So HIV is the reality. And this is the test result, right? This is also the reality. And these are the results of hypothesis testing, right? And so in that way, this picture is much more like sensitivity. And really, when we apply the word sensitivity, we see a whole new way of looking at power. Power is the idea, how sensitive is your hypothesis test? When there really is something to detect, can it detect it? When there really is HIV, can your test detect it? When the null hypothesis really is false, can your test detect it? That's the question that power is asking. Okay, so can we calculate power? Is there a nice little formula for it? Well, power is more like the tables in the back of your book. You can't quite calculate it with like one simple, straightforward formula. There is actually a more complex formula that does involve calculus. But we can simulate power for a whole bunch of different scenarios. And those scenarios all depend on alpha and effect size and also variability and sample size. And because of that, power is often found through simulations. So I'm not going to focus on calculating power, right? So we're going to say, sorry, let's not talk about calculating power. Instead, I'm going to try to give you a conceptual understanding of power. Now, often a desired level of power, and sometimes you may be working with computer programs that might calculate power for you. A desired level of power that you want to shoot for is 0.8 or above. But I want you to know, how does power interact with all these things? All of these things actually go into the calculation of power. But I want you to know this at a conceptual level. So how does alpha, or the significance level, affect power? How does effect size, D or G, affect power? How does variability, S or, S squared, affect power? And how does sample size affect power? Okay. So first thing is, how does alpha affect power? Well, here in this picture, I've shown you two distributions. You could think of this one as the null distribution, and this one as the alternative distribution, right? And notice that both of these distributions up here are exactly the same down here. I just copied and pasted it. Oh, yep. Right? Okay. The only thing that is different is not their means or the actual distributions. The only thing that's different is the cutoff. So here the cutoff score is right here, and this is the alpha, right? That's the alpha. And here, the cutoff score has been moved sort of closer towards the population mean, right? And now we have a huge alpha. So let's just assign some numbers here. I'm just guessing, but maybe that looks like alpha equals 0.05. That's something we're used to seeing. But this looks like maybe alpha equals, let's say, 0.15, right? Something like that. What happens when we increase our alpha? Our alpha has gotten bigger. What happens? What happens to power? Well, it might be helpful to think about what power might be in this picture, right? Remember, power is the probability of rejecting the null hypothesis when the null hypothesis is actually false, right? And here, we often reject when it's more extreme than the cutoff value, when your X bar is more extreme. So these are the rejection zones, everything on this side, right? So reject, 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 right? All of this stuff is reject. Reject the null. And we want to look at the distribution where the null hypothesis is false, aka the alternative hypothesis, right? So really, we're looking at this big section right here, right? So here, this big section, that's power, 1 minus beta. Given that, you could also figure out what beta is. Here's beta right here. And beta is our error rate for misses. When we fail to reject, right? Fail to reject, but the alternative hypothesis is true. Or the other way you could say it is the null hypothesis is false. All right, so what happens to power when alpha becomes bigger? Well, let's color in power right here. And it seems like there's more of this distribution that's been colored in than this, right? So this part has been sort of added on, right? It used to be just this equals power, but now we also have added on this section. So as alpha increases, power also increases, right? And hopefully you could see that from this picture. Now, imagine moving alpha out this way, so decreasing alpha. If we decreased alpha, then this power portion of the distribution, that power part will become smaller, right? So the opposite, sort of the counterpoint to this is also true. As alpha decreases, power also decreases. Great. Oh, but you might be asking yourself, oh, then why don't we just increase alpha so we could increase power, right? Well, remember what alpha is. Alpha is your false alarm rate, right? So if you increase alpha, you also increase your false alarm rate. So at the same time as you increase your false alarm rate, you're increasing power. Power is a good thing. False alarm rate, not so good, right? And so this often isn't a good way to increase power. But you should still know what the relationship is. Okay, how about effect size? How does effect size affect power? Well, remember, effect size is really sort of, you could think of it roughly as this distance between the x bar and the mu, right? We're really looking at that distance in terms of standard deviation of the population, right? How does effect size affect power? Here I've drawn the same pictures, right? Same cutoff, right? Except I have moved this this alternative distribution a little bit out to be a more extreme, so that we now have a larger distance, right? And so this is a bigger effect size. Bigger, let's say G, bigger effect size. So what happens when we increase effect size and we keep everything else constant? The cutoff, the null hypothesis, everything, right? Well, let's color in this and color in this. Which of these two blue areas is larger? Well, obviously this one, right? This power is bigger than this power, right? And it's because we have a larger effect size. So another thing we've learned is that larger effect size, it leads to larger power. So as you increase effect size, you could increase power. But here's the kicker. Can you increase effect size? Can you do anything about effect size? Is there anything you could do? Not really. Effect size is something that's sort of out there in the data, but you can't actually do anything to make it bigger, right? But you should know that if you happen to have a larger effect size, then you have more power than if in your study you have a small effect size.